Hey everybody, PCB Junkie here. Today I want to talk to you about a project that I've been working on for the last little while. It is a toaster oven, as you can see, that has been converted into a reflow oven. And this is an oven that I'm going to be using for SMT soldering. It's a project that I started, I think, back in 2017, and I've been working on it off and on, fixing bugs and making enhancements wherever necessary. But I hardly use this thing, and that's probably the reason why the development's taken so long. But nonetheless, here it is. I made a series of enhancements recently, and now with this thing being pretty functional, I thought it is a time to make a video about it and showcase this thing and see if there's any interest in making something like this available either as a DIY kit or perhaps as an open source, open hardware project. Before I open this thing up and show you inside, I want to give you a high-level overview of this project, why it even exists, and also we can briefly talk about some of the design choices and its functionality. This all started when I had an oven in the kitchen that broke down. The knobs got loose with age, and I wasn't able to control the temperature correctly or the timer. So I thought, the best thing to do with an oven like that, instead of tossing it out, was to turn it into a reflow oven, which was on my mind already, since I was doing a lot of electronics at that time. I wanted to get into soldering SMT electronics, and of course the most effective ways to do it with a proper reflow oven. I started to explore various options in terms of how to measure temperature, how to control the heating element, and I think I came up with a fairly decent design. And at that point I decided this is good enough for others to use, and I thought, why not create a controller that can be used to easily modify one of these things, which are very readily available, to create a fairly decent and functional reflow oven. So this is basically where we are. This is the project in a nutshell. As far as the design choices go, I ended up with a design that uses NTC thermistors for measuring temperature and a triac for switching off and on the heating element. I would say the cost was the most important design constraint when working on this project. If you're going to be using a toaster oven like this for reflow soldering, it probably means that you don't want to spend a lot of money, since you got this thing probably for next to nothing. And the last thing you'd want to do, of course, is to go out and buy yourself a whole bunch of parts, which may total as much as getting a device like this off the shelf that works out of the box. The NTC thermistors are very readily available, and they require very little circuitry in order to measure temperature. Now, they're not super accurate, and they're not accurate over a wide range of temperature, but for something like this they work quite well. We could use other temperature probes, but they would typically require a lot more circuitry that I just didn't think was necessary. So that's the first design choice. It's to use a 10K NTC thermistor. There's a little bit of information about thermistors and how to measure temperature with them on my website. The link is below. You can check that out if you want. But yeah, the choice there to use thermistors ended up to be quite a decent one, and I think this thing is pretty accurate. In fact, you can use two thermistors in parallel, various modes of operation. In fact, you can pick one or both and use them to measure the temperature inside, and it seems to work quite well. As far as switching the heating element, again, I explored various options. Some options like using a relay or a solid state relay just were overkill. Well, first of all, a relay at this type of amperage can get tricky. The contacts may stick, and it's not really necessary anyway to use a relay like that, which would be expensive to begin with. So The best option, of course, was to use a triac. It's you know, since we're only switching AC, it's really very effective for that, and it doesn't produce a lot of heat, and it's super reliable. It's solid state, nothing to break over time, and you will see that it works quite well in this implementation. As far as the capability of this oven, we have an LCD display that we can use to select the various functions. The most important function here, of course, is the reflow function. It allows us to select from one of the 4 reflow profiles, which can then be executed. And each one of those profiles can be modified and saved. It is in fact stored to flash permanently, and then it can be recalled for later use. There are also a couple of other functions available here. We have a couple test functions, as well as a configuration function that we can use to configure this oven. But we can talk about all that later when we actually do the reflow and configure a profile to use. And for now, I think this is enough of an overview. So let's crack this thing open and see what's cooking inside. And here's the reflow oven with its side opened. Let's talk a little bit about how this thing is hooked up. We have our mains coming in through these orange sleeved wires. One of the mains, I'm guessing it's probably the neutral, is attached directly to one of the heating elements. That goes off then and connects into the controller board. The second wire goes into the controller board as well. Now, one of these wires, the hot side, is switched off and on through this triac right here, and that is then hooked up to the heating element. So as you can see, that forms the switching circuit. That circuit is separated from the rest of the board, and it's also opto isolated. Now the AC goes through this transformer. It's a 12-volt transformer. It gets rectified by those 4 diodes over there, and then in the corner there you will see a LM317 voltage regulator with the appropriate resistors and capacitors, which then creates our 3.3 volt rail that powers the rest of the circuits. Now the main star of this board right here is the Texas Instruments MSP430 microcontroller, which is responsible for reading all the signals from the oven thermistors, which give the microcontroller reading of the temperature, and also controlling the fans as well as the heating elements. So the controller itself also gets a number of inputs, which, as you can see, have been wired to the front panel. We have the 3 buttons right there and our knob. Also, in order to display the information, we use a Nokia 5110 LCD display, which also is handled by the microcontroller itself. Now, with this board, I made an option to use either a Nokia 5110 or Hitachi, 1602 and 2002, which is 16 characters by 2 lines and 20 character by 2 lines LCD displays. And I wanted that flexibility because the various ovens that you may get, they may have limited real estate on the control panel here, and you may not be able to use anything larger. And of course, I wanted to give you guys a little bit of flexibility in what parts you use. So both are supported in this case. In this particular version, which is my test oven, uses the Nokia 5110. And I think that's about it. One more thing that I forgot to mention is we have 2 transistors, which are the fan controllers. So we have 2 pairs of transistors, and one of the fans right here is hooked up to the front panel, and it's responsible for cooling this heatsink, which is attached to our triac, and also the rest of the board, because as you can see, This thing is inside of this little space, which is on the other side of the hot part of the oven, and itself gets quite hot. So we need a little bit of cooling, and I wanted this whole project to be able to fit within the walls of a typical toaster oven. I didn't want anything that kind of sticks out, so everything had to be self-contained, and there is obviously now a need for a fan in order to keep the board itself cool. On the control panel of the Reflow oven, we have 3 buttons. We have our back button, our forward button, and our OK button. These 3 are mainly for cycling through the menu, selecting the various options using the back and forward, and then confirming the selection with the OK button. The spinner here is used to select, much like the back and forward buttons are, but this is mainly used whenever there's a lot of data entry that has to be done quickly, like for example during naming of a profile or selecting from a wide range of values. So in that case we would use the spinner. Now these 3 buttons are digital. They plug directly into the GPIO of the microcontroller. The microcontroller just reads these buttons directly. It does the debouncing as well. The spinner is simply a pot. It's as you can see, it only goes so far and then it stops. It's not an encoder, and this is done for simplicity's sake. I didn't want an expensive encoder. I just have a whole bunch of pots lying around, so that's the design choice that I made. And this pot hooks directly into the ADC input of the microcontroller, and the microcontroller can then, based on the resistance, determine where it is approximately, and that could be used then to select the various values. Now it's obviously not going to be as precise as an encoder, but in this particular case it works quite well. Now whenever you're working on a project like this, it's always pretty easy to screw something up, especially when you're connecting things together. Now in order to help with that, I implemented a couple of test functions. So we have here a test input and a test output function that we can use in order to make sure that everything is connected and working properly. So let's quickly go through these and I'll show you exactly what we can test with these. So let's start with the test output function. Now in here I can test either the heater or either one of the fans. This particular controller can handle 2 fans. The first fan is used to cool the triac that's mounted on the heatsink that I showed you earlier, and fan 2 can be used to cool the board that was just reflowed at a higher rate than normal. A lot of the soldering profiles recommend about 3 degrees per second cooling, and an oven like this won't be able to cool the board that rate. So a fan can be used to speed up that process. To test any of these, we can just simply select one and then we turn the knob, and then we'll be able to turn on to a specific percentage. So this is basically our intensity on is 100%, and then we can select a lower rate of intensity, and this is just simply generating a PWM signal. This particular signal goes into the triac to turn on and off the heater element, so that's why you see that light flashing. Now we can go ahead and select the fan. I'm not sure if you can hear it. And of course we can change the intensity as well. So that's pretty much it for the output test function. Let's step back and go into the input test. So here we can see the ADCs, the readings from the analog to digital converter. These correspond to the thermistors. So this is the temperature thermistor. and this is the secondary thermistor, which is not in use. And then here we have the board thermistor, the thermistor that's mounted on the heatsink, telling us how hot the board is. Now we can test the buttons by pressing the buttons. I can see that there's a change on the screen, and of course we can also do the same thing with the pot. So, and this will quickly allow you to determine whether the board is working and also the controls are working as expected. Before we discuss the functionality of the reflow oven, I think we should spend a little bit of time to talk about soldering profiles when it comes to reflow soldering. I pulled up here an article from Wikipedia called Reflow Soldering. It discusses the subject in detail, and it has a little bit of information on a typical soldering profile. Here's a diagram that I want to spend a little bit of time on. Now, as you can see in this diagram, we have the time axis right here, and then we have the temperature. And as you can see, the temperature follows a certain pattern. Why would you want to do this? Well, it's been proven that it builds the proper bond and solders the components effectively. So we're basically following this formula in the reflow oven, and this is exactly how we're going to structure our reflow profiles. Let's talk about each one of these stages in a little bit more detail. So the first stage is the ramp. So we basically increase our temperature at a specific predefined rate. As you can see here, typically this is from 1 to 3 degrees Celsius. And we increase this temperature in a steady manner until we get to the next stage, which is called our soak or preheat stage. And we maintain, during this stage, we maintain that specific temperature for a certain amount of time. The temperature here that we have may not be exactly what you need to do with your own solder. You'd have to check. But again, this is pretty typical. It says here that we maintain 150 degrees plus or minus 20 degrees Celsius for about 1 or 2 minutes. Once the temperature on the board stabilizes and the board is heated uniformly, we start to increase the temperature once again, and this is the ramp stage, and we do this at 1 to 3 degrees Celsius, and this is of course per second. So this temperature is increased up to the peak of our reflow. We call this the peak. We also call this point to this point, or this stage right here, the reflow stage. This is when the solder actually begins to melt. Once we hit the peak, we then start the cooling process. And again, the cooling requires a certain rate of cooling. Here it says 2 to 4 degrees Celsius. I want to spend a little bit of time on this particular stage. Normally within a toaster oven, if you're going to be doing this, you're not going to be able to get this type of cooling rates. With the door closed, a typical reflow oven will probably have something like 0.5 degrees per second when it is really hot, and as the oven cools, that rate decreases quite a bit. So a recommended rate, as we can see here, is about 2 to 4 degrees Celsius. In order to achieve this, a reflow oven should have a cooling fan installed. Is this really necessary? Well, not really. It's typically not even followed, I would say. So a lot of the times the board is just left to cool in the ambient air, and it cools slowly. But it seems like manufacturers do recommend a higher cooling rate, and apparently this helps the solder stabilize, and it forms a better structure. So in this particular case, with this reflow oven, we don't have a fan installed, so we're just going to let it cool by itself, let the board cool by itself. But I do recommend that you do install a cooling fan if you want to take this seriously. And of course, the controller board actually allows you to do that. There are 2 fan outputs. One is dedicated specifically to increase the cooling rate. So now that we've discussed reflow profiles, let's talk about how this particular reflow controller handles them. So a reflow profile is composed of a series of steps. Each one of these steps can be defined to be one of the 4 available functions. Let me show you exactly what I mean here. So whenever we're editing a profile, we'll be able to see a function right here. And this function is one of the 4. It's called ramp. What it actually allows us to do is it allows us to go up to a specific temperature, which is right here, 150 degrees, by a certain amount of change per second. So what this means here is that we're going to ramp up to 150 degrees at 1 degree per second. Okay, so that's exactly what that means. Now we can change that, of course. We can change that to be, let's say, a soak. So that's one of the other 4 functions. Soak means we stay at a certain temperature for a specific period of time. So here we have 150 degrees for 0 seconds. Of course, we can go ahead and change that to be anything we want, right? So that's the second function that's available to us. Now, in addition to those 2, we have temperature. And this is very similar to the ramp function, but instead of using a certain rate of change, we tell the oven to get to a certain temperature in a specific period of time. So here we have 59 seconds to go up to 95 degrees. Okay, so that's the third function. And finally, we have the cool down. And the cool function is basically the same thing as the ramp, but in reverse. So we're cooling at a certain rate down to a specific temperature. So those are the 4 functions that are available to us as far as creating profiles. And we're now going to go ahead and actually create a profile that we can then use to demo the reflow functionality of this oven. So let's go ahead and do that. So now I'm going to edit a profile, and I'm going to pick the 4th profile, which is just labeled as user 2. Of course, that can be changed. We can change the name to whatever we want. You know, if I want to make a change here, I just use the knob to select whatever I want. Let's call it user X just for convenience. And let's enter the edit screen, and now we're going to set up our steps that compose this profile, that this profile is composed of, I should say. Here we have our ramp up. This is the ramp function, as I briefly described already. We're going to use a 1 degree increase in temperature per second, and we're going to take the default 150 degrees here. Okay, so that's going to be our first step. Now we'll go to step 1, which is our preheat, and we'll use a soak function right here, but instead of using 190, we'll try something a little bit closer to 170, and we can do this, let's say let's make it 45 seconds. Okay, so that's our second step in the profile. So first step is ramp up to 150, then we're gonna stay at around 170 for 45 seconds, and then we'll go to the third step. This would be the peak in the reflow profile. This is when it actually melt the solder and connect the various components together. So we can set this to, let's say, we'll set it to, let's make it 200 degrees, okay? Or maybe let's make it 190 or something like that, just to keep things quick. Okay, so we have 190, oops. Let's go back here, instead of 45, yeah, let's keep it at 45 seconds. That should be plenty of time for the oven to be able to get to 190. And finally, our step 3, which is when the reflow would actually happen, we soak. So we stay at 100. Let's make it 190 again. for 15 seconds. Okay, so that's our step 3, and our step 4 is the cool down. So we'll keep the default 1.5 degrees per second cool down to 100 degrees Celsius. Okay, and that should give us a fairly quick profile that we can execute. And now we'll go ahead and save this, and we hit the OK button, and our profile should be saved. So I'm gonna go ahead and put the camera on the tripod, and we're gonna basically start this profile that we've just edited, and we're gonna watch the oven in action. Okay, now I'm gonna go ahead and start the reflow process for the profile that we've just edited. So I'm gonna enter the reflow function, and I'm gonna select profile 4, which we named user X, and the oven is gonna start to execute that profile. So here we are. Now at the top here we see that the first step is our ramp, called the ramp up. We're, if you remember, going 1 degree per second up to 150 degrees Celsius. Now the current rate, the oven is now heating up. We're at 0.4, and our current temperature is 59 degrees. And here we have the time that it's taking this step to execute. So yeah, we'll just watch the screen for a bit, and you can see that the rate tends to stay around 1.0 degrees per second. So the oven is basically turning off and on the heating element to try to stay close to this range. There's a little bit of thermal inertia, I guess, as the heating element turns off and on. It still ends up heating the inside of the oven, even though it's been turned off. So the oven is trying to figure this out, and trying to adjust the heating element to stay as close to that rate as possible. So we're approaching 150 degrees. Once we reach 150 degrees, the profile will enter the next step, which is our soak, if I remember correctly. Soak to 170 degrees for, I believe, 45 seconds, if I'm not mistaken. So we're almost there, 3 degrees left, and here we are. So yeah, we're going to 170 degrees for 45 seconds. So the oven's now going to hit 170, and then it will try to stay there. Now this is that thermal inertia that I was talking about. So the heating element was turned off at 170, but the oven still continues to warm up. I mean, that's just the reality of the situation with an oven like this. So we're almost at 45 seconds, and now we're at the next step, which is step 3, and we're gonna hit a peak of 190 degrees. So again, the oven is warming up. Okay, so we hit 190 degrees now, and we've moved on to the subsequent step, which is to soak at 190 for 15 seconds. We're at 13, 14, 15, and we've entered the final step, which is the cool down. And the oven will try to cool down at 1.5 degrees down to 100 degrees. Now, this particular oven is a test oven. It doesn't have a fan. With the thermal properties of this particular toaster oven, it's not going to be able to cool at that rate unless I open the door. So this is normally where your fan, your cooling fan, would be turned on to increase the cool down temperature. but this oven doesn't have one. So I'll just open the door and we'll speed up this process somewhat. As you can see now, the rate should be increasing. But still, even with the door open, you can see that it's still quite high. And that's pretty much as good as it gets. So we'll just let this thing run down to 101 degrees, and that should terminate the profile. And there you have it, a completed reflow. If you want more information, you can visit my website. The link is going to be in the description. However, when this video goes up, the information may not still be available. I had a bunch of information about this project on my website before, but I unfortunately lost it in the recent crash. It's a long story. Anyway, yeah, the information will eventually make it up there. As far as making this project available to you guys, I'm still not sure on how to do this. Maybe you can leave a comment. I'd like to know whether you'd like to have this as an open source project where you make your own PCB and then compile the software yourself, put everything together, or maybe something like a kit is more appropriate for a project like this. Okay, this is going to be it for this video. I hope you enjoyed this, or at least found it somewhat informative. And if you did, let me know in the comments. Okay, thanks for watching everyone. I'll see you on the next one. Bye now.